Hello, my name is Fatemeh Nikbakhtnasrabadi and I'm PhD student at James Watt School of Engineering at University of Glasgow. So I will be presenting on the paper titled Flexible Strain Sensor based on printed LC tank on Electrospun Piezoelectric Nanofibers to the session on bio and wearable electronics. My presentation is divided into 4 main sections. I will start with a short background of this work, then I will look at the design and fabrication aspect. Next, I will go through experimental result of the developed sensor. Finally, I will outline the conclusion of the current research. So if we look at the background of this work, piezoelectric polymers with inherent capability to measure dynamic pressure have become popular choice for flexible and conformal biomedical devices. For example, our group have previously developed graphene-based field effect transistor coupled with biodegradable piezoelectric material for wearable application. We have been investigating other novel flexible material. However, patterning of this material can be difficult, and that's where screen printing comes in, which is very common, high throughput and easily scalable method for patterning flexible materials and very well suited for development of future flexible electronic devices. In this work, we are presenting all printed flexible LC resonator in which a sensing capacitor is connected to an inductor forming LC tank resonating at frequency of interest. The sensing mechanism is that the interdigitated capacitor is printed on piezoelectric nanofibers, and applying pressure on the capacitor alters the relative permittivity of the substrate, leading to changing capacitance. This causes a shift in resonant frequency of the LC resonator, which can be detectable when external reading coil comes to the picture. In this way, the LC tank allows us to monitor wirelessly applied pressure in real time. So as we can have a brief look at how our nanopolymers-based device looks like, in this work, we are developing a screen-printed interdigitated capacitor based on PLLA piezoelectric material using electrospinning. On the top left, we can see a SEM image of the Electrospun PLLA nanofibers, and on the top right, we can see a SEM image of a stretchable silver paste. Optical microscope images of a random finger of the interdigitated capacitor and the corner of inductor traces shows the overall quality of the printed devices. Next, our overall fabrication step to allow screen printing of the device. The first step is to prepare PLLA solution to get uniform nanofibers. To do so, a suitable amount of PLLA is dissolved in DMF and DCM solvent and steering well with a magnetic stirrer until the polymer is completely dissolved. Next, to make a thin membrane of well-aligned PLLA nanofibers, the electrospinning machine is running at 50 kilovolt with a drum speed of 2000 RPM. The realized membrane is highly flexible and has a porous structure that can interact well with soft human tissue because they are breathable and can conform to curvature in the case of use in epidermal application. So the next step is actual screen printing, which is done using a commercial silver paste with a semi-automatic screen printer. This patterning method can be just easily set very quickly to create really complex design. Finally, we end with curing the device in oven for 30 minutes at 130 degree. So we finish with a very flexible and polymer fully polymer screen printed device here. Next, we characterize separately the printed interdigitated capacitor and the inductor using an impedance analyzer to check capacitance response over a big range of frequency. As shown in the inset figure, the capacitance is around 80 picofarad at 30.46 megahertz, which agrees well with the simulated value. It was observed that the capacitance was almost constant over 0 to 25 megahertz frequency range. At 30.56 megahertz, which is our working frequency, is far below than the resonant frequency, self-resonant frequency. The sensing capacitor can be considered as a dynamic sensor for this frequency. So then the pressure sensing principle, as I explained it before, relies on the fact that the applied pressure changes the relative permittivity of the PLLA nanofibers, leading to the change in capacitance. The change in capacitance will shift the resonant frequency of LC circuit, and it can be monitored wirelessly through the inductive coupling with an external reader coil. To explore that, the interdigitated capacitor was characterized using a standard electrodynamic vibration system. Dynamic pressure in the range of 0 to 797 Newton was applied on the surface of IDC. This figure shows the change of the capacitance of interdigitated capacitor as a function of applied pressure. The sensitivity of this piezoelectric IDC was calculated by dividing normalized change of capacitance by the nominal applied pressure at the frequency of interest. As shown in the figure, the slope is not linear, so we define sensitivity for each interval. For the dynamic pressure less than 2 kilopascal, the sensitivity is 8.55 per kilopascal. The sensitivity in the range of 2 to 4 kilopascal and 4 to 7 kilopascal are calculated as around 31 per kilopascal and 8.6 per kilopascal respectively. As I mentioned earlier, the aim of this work is to monitor dynamic pressure wirelessly. So the printed inductor is also designed to establish a LC tank along with the capacitor when they are connected in parallel. The measured value of inductance at the frequency of interest was around 7.75 microhenry, which is very close to the simulated value. The measured value of resistance at the same point was around 367 ohm. The average quality factor obtained from 3 samples was 1.81 at the frequency of interest. It is noted if we compare the quality factor of printed inductor to conventional copper inductor, a copper inductor with the same geometrical parameters has almost 30 times higher quality factor. So the conductivity of traces plays major role in performance of inductors. And this kind of initial data shows that hopefully we can use this device as a wireless pressure sensor in future. In conclusion, we developed a fully printed LC resonator based on piezoelectric nanofibers with sensitivity with sensitive capacitor to dynamic pressure. It could be used as a simple bandage for wireless monitoring of pressure, like measuring pulse rate on a specific area of the body without any need of local power and complex circuitry design. Finally, a big thank to our funding sources, and also I would like to thank all of you for attending my talk today in IEEE FLEPS 2021 virtual conferences.